Okay, so this is lecture 5 on the proof complexity course, proof complexity as a computational lens. Let's start by reviewing what we did last time. We looked at the clique coloring formula, and this formula encoded that there is an n-vertex graph where n was our parameter, which had both an m clique but was also m-1 colorable, and we chose m to be polynomial in n. So m was like n to the delta for some delta. And we proved a lower bound via feasible monotone interpolation. What was this? So we proved that given a resolution refutation of this formula, we could extract efficiently a circuit that distinguished between these two cases. So you could, the circuit could tell, given a particular graph encoded by its edge indicator variables, the monotone circuit could tell whether the graph had an M clique or whether it was m-1 colorable, given the promise that at most one of these cases apply. But then we have monotone circuit lower bounds. Such circuits, if you pick m to be a suitable polynomial in n, this is exponentially hard for monotone circuit. And since the extraction of the monotone circuit from the resolution proof was efficient, the circuit had essentially the same size as the resolution proof, that gave us a resolution lower bound. So that was what we did last time. And now the question that we're doing today, natural question is well, what if we fix the graph? So we just fix the edge indicator variables, and then we get a graph, and we know that either the graph is not going to have an M clique or it's not going to be m-1 colorable. Or both, but this gives us then, as we said last time, once you fix the graph, the formula splits in two, and this means that you can consider lower bounds for graph coloring or lower bounds for formulas encoding graph coloring or lower bounds for formulas encoding clique. So graph coloring, we have strong exponential lower bounds. For resolution, we'll see, in fact, we won't do the resolution lower bound, we will do the polynomial calculus lower bound slightly later in the course. And these are, in fact, the strongest possible bounds because we will prove even on average coloring is hard. So there's a natural random distribution on graphs. I can sample graphs randomly. They won't be, say, 3 colorable, and yet it is hard for resolution and also for polynomial calculus to decide that the graph is not 3 colorable. So graph coloring we understand pretty well. But now you can ask about clique, and that's what we're going to talk about today. And clique is much less well understood. And this is a little bit intriguing. Because we do have some understanding, or at least some intuition about the clique problem. And we do have strong evidence that it should be very, very, very hard. And unless proof systems are doing something very surprising, that means that we should have lower bounds for proof systems, but we don't. So let's see, let's just make sure that we are on the same page, that we know how are we encoding the clique problem. So we'll get to, sooner or later we'll have to write down the CNF formula. I'll defer that for a little bit. But the clique problem in general is just we're given an undirected graph G. And let's say this is a simple graph without multiple edges or loops or anything like this. The question is just, does G contain a k-clique? Just to make absolutely sure we're on the same page. So this is a subset of vertices, say capital K, such that for all U and V that are in K and that are distinct, UV is in H. So we're given a graph and we just want to say, can we pick out a subset of K vertices, capital K, of size lowercase k, such that they're all pairwise connected? This is the question. So what do we know about this problem? Well, we know that it's solvable in time, well, n choose k times some polynomial in n, right? And this is the obvious algorithm. You just try out all possible candidate k-cliques, and for every k-clique you check whether it is a k-clique or not. And if you find a k-clique, you say yes, otherwise you say no. Okay. We can do slightly better than this. It is possible, it is known algorithms that run in time n to the omega k over 3, where omega is the matrix multiplication exponent. Matrix multiplication exponent, which is, you know, what is it? Somewhere around 2.37, something like this. But this is basically, so you know, n to the actual k is not the best lower bound, but a to an exponent that scales linearly with k is the best we know. And what do we know more? Well, we do believe that clique is hard on average. And again, you can sample from a suitable random graph distribution. It's hard to tell whether graphs have a k-clique or not, meaning it's not just that this problem is hard for weird special cases. It's like it's a typical instance is hard for k-coloring. And we also have results saying that basically, well, if P is distinct from NP, then not only is it hard to decide the problem exactly, but even getting a meaningful approximation of roughly how large the largest clique is very hard. So from a theoretical point of view, this is just believed to be a dead hard problem. It is, I think, fairly widely believed that for any type of algorithm, we have an n to the big omega of k lower bound. So what does this notation mean? So this just means that there is some universal constant delta such that the complexity is n to delta k for n large enough. So basically, or phrased differently, like n to the big omega of k. What I mean by this is that there is some universal constant delta such that running time is big omega of n raised to delta times k. So this is like a standard abuse of notation. This lower bound holds if the exponential time hypothesis is true. So if the SAT problem, Boolean satisfiability problem, deciding whether a CNF formula is satisfiable or not, if that requires exponential time, this is the exponential time hypothesis, ETH. If that is true, then clique has essentially like the stupid algorithm is best possible up to constant factors in the exponent. And then, as we talked about in the first lecture, if you actually want to solve clique in practice, because clique does appear in a lot of settings, for instance, in computational biology, then there are, in fact, very good max clique algorithms. So this raises the question again: can we actually, like, can we know that these algorithms don't actually solve k-clique in polynomial time? That would somehow be a nice thing to prove, unconditional. So the question is, do we have unconditional results for some kind of bounded computational models? Obviously, we can't prove n to the big omega of k in general. That would separate P and NP, and then we should probably write up that paper. But at least for bounded models of computation, you can ask what we can do. We do have lower bounds for bounded depth circuits in circuit complexity. This is results by Rossmann. So for bounded depth circuits, we have n to the big omega of k. For monotone circuits also, again, n to the big omega of k. It's natural to ask, since we talked about proof complexity, one view of proof complexity is that it models concrete algorithms. You can ask, can we, for some interesting proof system, prove n to the big omega of k lower bounds? What about resolution, for instance? Okay. Or what about if we look at some state-of-the-art max clique algorithms? Can we look at what they are doing and model that at some kind of proof system and prove lower bounds for that proof system? Okay. So what the spoiler alert, what we're going to talk about today, and this is going, we'll make this more formal later. So here comes a very informal theorem. So the informal theorem says that suppose that I'm interested in k-cliques, but for k smaller than square root n. So asymptotically smaller than square root a. So for such a k, and for a random graph G sampled from some suitable random graph distribution that I'll obviously have to tell you about, it holds asymptotically almost surely that A, G doesn't have a k-clique, but regular resolution requires length n to the big omega of k to prove this. Okay, so this is what we're going to talk about today and also next time. As a corollary of this, you get that for, depending on how aggressive you want to be in your marketing, you can say for essentially all state-of-the-art algorithms, you can tone it down a bit and say, well, at least for a large and interesting fraction of state-of-the-art clique algorithms, a lower bound for regular resolution is strong enough to give the same lower bound for the algorithm. So this means that for a wide class of the best algorithms out there in practice that are actually known and used today, n to the k, except for content factors in the exponent, is the right bound. And I should say that when we claim that regular resolution models these algorithms, it's up to a 2 to the k factor, because these algorithms typically can count efficiently and resolution cannot count efficiently. But the point is, you don't need to worry about the 2 to the k loss because that's dominated by n to the k. So I'm not even going to elaborate on the algorithmic connections from now on. We're just going to go for this proof complexity. So there are three things that I need to tell you about in order to make sense of this result, or at least I can think of three things. I should explain to you what I mean by random graph. I should probably explain what regular resolution is. And also, what does it mean that regular resolution proves something about k-cliques? I mean, regular resolution doesn't prove anything about clique or coloring or anything, right? It's given a formula and it reasons about this formula. So I have to tell you about the encoding. Okay. So my plan is to now tell you about these things. So from now on, we're just gonna, so we'll spend a part of today to figure out what we mean by random graphs, what is regular resolution, how are we encoding the clique problem, and then we'll try to see some known lower bounds, some known upper bounds, we're going to start to do a lower bound, and then we're going to fail, and then we'll get very depressed, and then we'll try to fix it, and then we'll run out of time, and then we'll meet on Monday and hopefully give the full proof. That's the plan. Any questions before we start implementing this plan? Or are we feeling completely happy? I feel that you guys are just radiating happiness. So let me start right away. Okay, the graph distribution is going to be Erdős Rényi random graphs. What is this? I think many of us know, but so we have an n-vertex undirected graph. And we're just going to include every edge independently with probability p. Okay, so when you have an n-vertex graph and then you flip a p-biased coin for every edge, there are n choose 2 possible edges. For every edge, you just flip a p-biased coin. If it comes up heads, you take the edge. So you take the edge with probability p, with probability 1 minus p, you say this edge is not in the graph. So we'll just use, this is all standard, this distribution, we're going to write it fancy style G of n and p. Okay, so what do we know about this? Well, if you fix a K of a set of vertices capital K of size lowercase k, then the probability over the random sampling that K is a k-clique is exactly p raised to the power of k choose 2. Right? I mean, it is a clique precisely if I pick all of the k choose 2 edges. Nothing strange there. So the expected number of edges that n sub k be the expected number of k-cliques, that will then be n choose k times p raised to k choose 2. Just by linearity of expectation, I consider all candidates. There are n choose k candidates for every candidate. The probability that this particular subset of vertices is a k-clique is p to the k choose 2. So this is going to be the expected number of k-cliques in a random graph. And now, if you do the math, and I was not planning on doing the math, but if you just plug this in, you realize that for p n to the minus 2 over k minus 1, you will get that this expected number of cliques is 1, give or take. Right? You just set this to 1 and solve. Okay. So this is a interesting edge probability. So you should think of when we're interested in k-cliques, the interesting edge probability is n to the minus 2 over k minus 1. That's sort of, there we're finally balanced as to whether we will have k-cliques or not. As in most Raft random processes, there's sharp concentration, meaning that if we take a slightly smaller edge density, then we're not going to have a k-clique. No way, no how. Except with exponentially small probability. Okay, so what we're going to do is throughout today, we'll let eta be some constant that is larger than 1. And you should think of, unless otherwise stated, we should now pick edge density minus 2 over k minus 1, except I multiply by eta. Okay? And since eta is larger than 1, unless I'm messing up, this means that the edge density goes down ever so slightly. But think of eta as a constant for now. I'm going to, in the proof we're doing, actually, if you read the paper, they're like very fine-tuned results for eta varying. I'm not going to do that. I'm just going to fix eta to be a constant and get like the main message across. The point is that if I fix such an eta, then the probability that the graph contains a k-clique, the probability that the number of cliques is larger than 1, is by Markov's inequality is smaller than, well, the expectation of this variable, which by the math over here goes to 0 when n goes to infinity. Okay, so this is going to be, this is an interesting edge probability in the sense that we're sure that there is no k-clique, but we have many big omega of k-size cliques. So there are going to be lots of smaller cliques, cliques of size, you know, I don't know, k over 10 or something like this. So the idea is that it's going to hopefully be hard to, you know, there are lots and lots of fairly large cliques, but there's no k-clique. And we're hoping that this will be a hard distribution. Make sense so far? So good. So this is what we mean by random. Regular resolution then. What's regular resolution? Well, let's recap what, okay, so resolution, there's, you know, we have a CNF formula. We want to derive contradiction from it. There's one derivation rule. Let's just write it down because it's maybe a little bit odd to do a lecture about resolution without writing down the resolution rule. So from, if I have clauses on the form C or X, D or not X, then I can resolve over X and get C or D. I think of all clauses as just sets of literals. So there are no repetition, order doesn't matter. And I can apply this rule iteratively over the clauses in my input formula until I derive the empty clause, which I denote by bottom, which is contradiction. Okay, we all know this by now. Now, and when you think about like, how do I apply this rule, then it's natural that you sort of get a graph structure, right? Anytime you resolve two premises to get this resolvent, we can view this as every clause in the proof will be a node in a proof DAG, and then I add arrows just to indicate resolution steps. So now proofs come with directed acyclic graphs, and general resolution is the proof DAG is without any restrictions. In general resolution, the proof DAG can be anything. Then we have talked a little bit, and we will talk more later about tree-like resolution. There, the proof DAG is a tree. It's a binary tree. Okay. And one thing that we have talked about a little bit, but not used so much, I think, is that actually tree-like resolution, you can view it as isomorphic, almost as equivalent to the decision tree model. What's a decision tree? A decision tree is a binary tree that every non-leaf node queries a variable, and then there are two outgoing edges, 0 and 1. So given an assignment, you just start at the root, look at what the queried variable is, follow the edge that is labeled with the right value. So every truth value assignment just defines a path through the tree, and the decision tree solves the CNF formula F, or it solves the falsified clause search problem for F. If whenever you follow, like for any alpha, when you follow the path defined by alpha, you hit a leaf, that leaf is labeled by a clause that is violated, that is falsified by alpha. Okay. And whenever you want to think about tree-like resolution without loss of generality, you can think about these decision trees, they're the same. Okay, this requires a proof that we won't do, but it's an extremely strong equivalent. But what is regular resolution? So regular resolution is the following. So we still have a proof DAG. It doesn't have to be a tree, but in the proof DAG, along every path, any variable is resolved at most once. Okay, so I don't know. So suppose here is maybe like a proof DAG, and let's suppose that this is we start at some input axiom, and then we just trace a path. This goes via a lot of resolution steps until we hit contradiction. And obviously at each node in this path, you can ask, like, what variable did I resolve over? And a path is regular if I never repeat variables. You only resolve over a variable at most once. Maybe you don't resolve over it at all, but at most once. And a proof is regular if all paths are regular. Okay? And on the one hand, okay, and regular resolution, again, the proof is DAG-like, so you can prove that regular resolution is exponentially stronger than tree-like resolution. Not going to do this, but for instance, later in the course, we're going to talk about pebbling formulas, xorified pebbling formulas. Xorified pebbling formulas are an example of a very strong exponential separation between regular and tree-like resolution. Now you can ask, what about regular resolution and general resolution? Is there a difference? Okay, and I think it's fair to say, so the very first paper that I'm aware of that actually did like proper proof complexity about resolution, that's Satin's paper from 1968. He considered regular resolution. And I think, I wasn't around at the time, but my understanding is that if you think about the regularity condition, then basically suppose you're resolving over X, here. Okay? That sort of means that obviously you want to get rid of all the variables, yes? So at this point you resolve over X, you get rid of X. Okay. Would you somewhere later in the proof, would you want to reintroduce X again? Like you've gotten rid of it, right? The goal is to shrink all the clauses, so it seems that it would be a bad idea to resolve in such a way that a variable that you worked very hard to eliminate appears again. Like, why would you do that? That's self-harm. And so, in fact, for most formulas that you will ever run into, like the proofs you're coming up with will be regular proofs. And there are conjectures to the effect that for large classes of formulas, regular resolution is basically without loss of generality the best you can do. Because somehow I would make the argument like any proof you can ever come up with is a regular proof because it's such a natural thing. Like you try to get rid of variables. Okay? There's only one problem. Regular resolution is in fact exponentially weaker than general resolution. There are some examples of this. They're typically quite convoluted. You have to think really hard to come up with a formula that is hard for regular resolution. The examples are not natural at all. And I don't think we will talk about this in this course, or at least I'm not planning to. But somehow there are a few results in the literature, including Satin's first lower bound for, Satin formulas, where you have the example that you first prove a lower bound for regular resolution, and that sort of morally tells you what the result should be, and then you have to kill yourself and work much, much, much harder, and then finally you get it for general resolution with a lot more pain. This is obviously, again, this is not always true. We do have separations, but for instance, for clique formulas, there's no real reason to believe that going non-regular would help you in any way. But of course, we don't know. So it's very annoying. Like we'll only do the proof for regular resolution, and we will use the regularity condition heavily in the proof. And the first open problem is right there. As you listen to everything I do today, like get rid of regularity. This should be possible. Morally, clique doesn't say anything about regularity. There should be exactly the same lower bound, but for general resolution. The only problem is I don't know how to do it. But you guys are smarter, so you will do it. Is the hope. That's why I'm giving this picture. Now, one thing that we're going to use, I said that tree-like resolution is the same as decision trees. Turns out that regular resolution is the same as so-called read-once branching programs. And this is kind of a helpful model, a helpful way to think about resolution. So let me maybe let me talk about what a branching program is, and then let me tell you what the read once restriction is. Okay, so what is a branching program? A branching program is a directed acyclic graph. It's a decision tree, except it's not a tree. Okay, so there's one source node without incoming edges. That's the start. And then every non-sync is labeled by some variable x. Like this, and then you have two outgoing edges, 0 and 1. So again, given a truth value assignment, if you come to this node, you say, we now want to know the value of x. And if x is 0, you're going to walk along this edge. If x is 1, you're going to walk along this edge. So any truth value assignment will define a path through your branching program until you hit a sync. And every sync node should be labeled by a clause. And the point is that a branching program solves the falsified clause problem for a CNF formula F if the path defined by alpha reaches a sync that is labeled by some C such that alpha falsifies C. Okay, and the size of a branching program is just the number of nodes. Okay. And now I'm going to repeat this later also, but that means that we're going to talk about branching programs or proof tags, but we also have a clique graph that we're talking about cliques in. So I'll try to be consistent there. Whenever I say vertices, now we're talking about this graph G that does have or doesn't have a clique. Resolution isn't quite sure about this, but it's trying to figure it out. And whenever I say nodes, I'm going to talk about the branching program. Okay. So the only thing I didn't tell you about is what is read once. Let me write it here. So read once is the property that along any path, any variable is queried at most once. Okay, so we say this when I hit this node, they say this node queries x. So branching program is read once if for all alphas, when you look at the paths defined, you will only query any variable at most once. You're not allowed to re-query. Does it make sense so far? Okay, so now so why are we talking about branching programs? Well, we can make two observations. Again, I'm actually let me first make an observation about general resolution. So I claim that a general resolution proof, if someone gives you a good general resolution proof, that gives you a branching program of the same size. Right? How do I do this? Well, my start node is contradiction. I flip the direction of all the edges. What variables do I query? The variables resolved over. Okay, so it's clear now that any path is going to hit an axiom, and by my way of defining things, oh, I didn't tell you when, which, I mean, okay, when you are at the resolution step and you resolved over X, which one is the 0 edge, which one is the 1 edge, you walk to the premise that contains the literal that is falsified by your assignment. Okay, so if you define it in this way, then when you flip a resolution proof around, any truth value assignment will just define a walk over falsified clauses, just by induction, until you hit the sink, which is an axiom, which is then by induction falsified. Okay. So this means that if I want to prove general lower bounds for resolution, I can just prove lower bounds for branching programs. Right? Great. Except branching programs are super strong. So this doesn't work. Branching programs are much more powerful in general than resolution proofs. That's bad news. However, if you think about it, by now you should be maybe not super surprised if I tell you that regular resolution proofs give you read once branching programs. Read once branching programs. And if I run out of energy from now on, I just say ROBP for read once branching program. Okay. And now, in fact, we can say more than this. We can actually say that these are the same. This you can prove in the same way that decision trees and tree-like resolution are essentially the same object described in different ways. A read once branching program and a regular resolution proof, like there are translations back and forth, lossless translations. I'm not going to prove this because we don't need it. We only need this direction. That from a regular resolution proof, we do get a read once branching program. And this, I claim, is like I told you what to do, right? You just start in contradiction, you flip all the edges, you walk along falsified clauses. How do I know that it's read once? Well, it's the regularity property, right? I resolve over any variable at most once. That means I query any variable at most. So from now on, you should be convinced that if I can do a read once branching program lower bound, then we have a regular resolution. Okay, so therefore I only do this direction, except I'm going to cheat a little bit because we are going to do some upper bounds, and then I'm also going to use this maybe.
Sorry, what?
Nicer to express the upper bounds in this language, but it's like it's a paper that says that these two are equivalent, and I don't want to elaborate too much. Was there a question?
Yeah, so you said regular resolution is exactly characterized by ROBPs, but branching programs do not characterize resolution. What is the proof system that corresponds to branching programs?
That's a great question. I mean, branching programs are strong. And I think I don't know if there's a good characterization.
Okay.
And I think one way of maybe seeing the difference is that a resolution proof tag has the following property: that suppose I just tell you that you have an alpha in mind, and I'm just saying I don't have the energy to look at this whole proof tag, but look, here somewhere in the middle is a clause that is actually violated by alpha. Start walking from here. then the resolution proof branching program has actually, if you think about it, it has the guarantee that starting from anywhere in the branching program, from any falsified clause, will give you a legitimate answer to the search problem. Is this making sense?
Yeah, I think.
And the general branching program has no such guarantee at all.
Mm-hmm.
Yeah, you really need to stop.
Okay. Mm-hmm.
Okay, so what have we done now? We've talked about what random means, talked about what regular means. Let's maybe talk a little bit about encodings. I'm very happy with this. I'll save this board for the clique formula. So there are different ways of encoding the clique problem. And for some of the references that I'm just going to flash and that you can look up, there's a discussion. There are like several different encodings. And then there is a somewhat artificial encoding, or artificial at first sight, which captures all of these encoding. And the lower bound I'm going to tell you actually works for this general encoding that captures all the other encodings, except that we don't have the energy to explain this. So I'm going to give you like one encoding that I'm going to argue that it's very natural, and then we're going to forget parts of that encoding, and then we'll do a proof that contains like all the fun stuff anyway. Okay? That sort of gets all of the interesting stuff across, and then if you really want to see the details I'm cheating you on, then you'll have to read the paper. Okay, so I'll think of, so what is the clique formula that we're going to consider? We have a clique formula over G, and we have a clique size. There are two parameters, the graph and the clique size, which today is going to be K. And I think of the vertices as being just 1, 2, all the way up to n. Okay. So the first, and now we have variables, and we think of variables as you've seen before. XVI just means that vertex V is the ith member of the clique. So V ranges over 1 up to n, I ranges from 1 to k. And the claim that some vertex is the ith clique member is just this. Okay, so you have such a clause, a wide clause for all clique indices, I from 1 up to k. So these are the clique axioms. Then there are edge axioms that basically says that, well, if U and V, it says the following, that either U is not clique member I, or V is not clique member J, for I distinct from J, and for UV not being an edge. And in particular, we'll include here, if U and V happens to be the same, then also there is no edge, because we said there are no loops. Okay, so if you look at only these two, then there's no way of satisfying these constraints without having a clique. So in fact, the upper bounds we're going to do are just going to use clique axioms and edge axioms. But now you can see, if you actually want to solve this, then we can maybe be a bit more helpful. So we can add functionality axioms. The functionality axioms will say that that the ith clique member is a unique vertex. Clique member I cannot be both U and V. I don't need this to make the formula unsatisfiable if there isn't a k-clique, but suppose I'm running an algorithm like a SAT solver, this might be helpful, right? Because it decreases the search space. And also, if I want to decrease the search space even more, I could say that, let me write down. I can say the following. Suppose that U is less than V, for UV being an edge. But suppose that I is strictly greater than J, then I can say, well, if you want to have U and V both in the clique, then actually let the smaller vertex have the smaller clique in it. Like, why not? This is a kind of symmetry breaking axiom, if you like. Okay, so how interesting the clique lower bound is depends a little bit on how many of these you cover. Okay. Now, there's a standard way of defining a so-called clique block formula that just takes care of all of these. Maybe I'll just say, basically, you divide the vertex set up into k chunks, and you just say that the first clique member has to come from block 1, the second has to come from block 2, the third has to come from block 3, then you automatically satisfy the ordering axioms, and we can just remove them. And now you can say, well, if the graph doesn't contain a clique, then it definitely doesn't contain an ordered clique. But the graph could contain a clique, but not an ordered clique. So refuting the ordered clique formula is kind of easier. Refuting the block clique formula should be easier. And we can actually prove a lower bounds for such block clique formulas with exactly the same techniques, but it gets a little bit messier. And I think by the end of the second lecture on clique formulas, I think we're going to agree that things are messy enough as they are. So I'm just telling you that we can do this for ordering axioms, but from now on, I'm just going to blissfully ignore them. But like consumer information, this is the encoding that we want to deal with. And just for simplicity of exposition, we're going to ignore the ordering axioms. And I should say that even without ordering axioms, like any lower bound for just clique, edge, or functionality axioms, or really any good lower bound for just clique and edge axiom is still like super interesting. It's not like we know how to do lower bound for clique and edge, but then you throw in functionality and it's hard. That's not the way it is. So I'm just saying, like, this is that I would argue that these 4 classes of axioms, that's a natural encoding. The ideal scenario would be to do the lower bound for this, but lower bounds for other just partial encodings would also be super interesting. So what we're going to do, and so let me now try to state a formal theorem, somewhat formal theorem. And this is due to Atserias, Ilario Bonacina, our very own Susanna de Rezende, Massimo Lauria, myself, and Alexander Razborov. And basically we say the following, that for any constants, epsilon and eta, and that the full theorem statement is actually considering when these guys are moving around a bit, but I don't want to discuss that. So fix these constants, suitable constants, and suppose that G is a randomly sampled Erdős graph over n vertices. And again, the edge probability should be just below where we get k-cliques. So -2 times eta over k minus 1. We have asymptotically almost surely that G doesn't contain a k-clique, but regular resolution requires length n to the big omega of k to prove this, where this big omega will depend on epsilon and eta. And I think later, when we actually prove the full theorem, we might give a precise statement of this, but it's not too important. We are going to do the proof from the 2018 conference version. This is the simpler version that ignores the ordering axioms. And then there's a 2028 journal version that has the full details. But really, I should state here that we have k less than n square root n, so n to the 1/2 minus epsilon. That's kind of it. Actually, let me write down the conference version. Okay, let me do this maybe a little bit more carefully. The conference version gets k less than essentially square root n without ordering axioms. The full journal version, I think we get up to 4th root of n with a full encoding. That can do ordering. In fact, there's the clique block encoding, which can also take care of some other encoding. But we're going to do this conference version because there's nothing really fun happening. Maybe my suggestion, I wanted to talk to like 5 to 10 minutes about what we know in terms of lower bounds. So maybe are you fine with, or can we work for 10 more minutes, just figure out what is known, and then we'll take a break, and then after the break, we'll just do the lower bound to sort of, then we switch gears. Okay. So by now we have several different descriptions of resolution. We've also talked about this prosecutor-defendant game. And it's kind of not so important whether you think about prosecutor and defendants, or whether you think about branching programs or decision trees. So but since we talked about prosecutors before, maybe that's what I'm going to do for the upper bounds. So obviously, I'm cheating you a little bit because we didn't prove that regular resolution is equivalent to regular resolution is equivalent to read-bounds branching programs. I didn't prove to you that tree-like resolution is equivalent to decision trees, but it's not too hard. So we'll just, between friends, we'll skip the details. Or maybe we'll put it on a problem set. It's kind of a nice exercise. What do we know for tree-like resolution? Well, it's worth noting that already for tree-like resolution, we have an upper bound n to the big omega of k. So we believe that this is essentially best possible, or already tree-like resolution can do it. Why? Well, think about it as a... so basically, the way you can think about it is you can basically build a decision tree that queries all n choose k candidates. It just systematically starts querying all candidates. So it's like, you pick a subset of variables that you're interested in, and then you will query all clique indices for these variables. And now one of two things happens. Either the defendant says, no, that's not the clique, then you move on. If the defendant says, yes, this is the clique, then what do I know? I mean, then if the defendant has given answers that this is a clique, well, if it doesn't have a clique, then there's a violated edge axiom. So now you just, then you can terminate and get a leaf labeled by that violated edge axiom. So that's essentially what the upper bound is. I'm doing this a little bit quickly, but there's not much more to it than that. There is a lower bound, n to the big omega of k, for Erdős Rényi random graphs with appropriate parameters. And this is due to Beiersdorf, Olaf Beiersdorf, Nicola Gallesi, Massimo Lauria, 2013. Basically, again, so we're doing tree-like resolution. So this is the prosecutor-defendant game with the prosecutor never forgetting anything. So basically, one way to think about this lower bound is, well, if you sample a random graph, it doesn't have a k-clique, but it has, say, like a 10 over k-clique. In fact, it has many such cliques, like tons of them. So they're like, essentially, for some k prime, there's n choose k prime different small cliques. And this is just a fact of random graphs. And the way you see it is that, well, I mean, this value, if you lower k a bit, then this will be a supercritical edge density for a smaller k. That's sort of the way to see this. Okay, so there are going to be tons of cliques of size big omega of k in this graph. The defendant just picks one. Okay. And whenever prosecutor asks about a vertex in that graph, you say yes, unless you're contradicting previous answers. Like, for instance, if you're already committed to another clique index for this vertex, then you say no, or if you something like this, or if you already said that no, yeah, if you're committed to another clique index for this vertex, or if another vertex already is occupying this clique index, then you say no, but otherwise the first time, like V is in the clique you chose, and and acknowledging that V is clique member I doesn't yield immediate contradiction, you just say yes. Okay, this is the defendant strategy. Okay, what do we know when the prosecutor reaches a winning position? Well, the prosecutor will have identified exactly your k prime clique. Because as long as the only time as long as you're playing according to your clique, you're going to be fine. There can be no violation, because everywhere else you just say no, right? And all the other axioms are happy with no answers. The only guy that is unhappy are the clique axioms. So when I'm playing according to this strategy, I'm only losing by not setting a clique axiom. Why am I answering that all vertices that are not clique member I? Well, because I've already used up, all the vertices in my small clique have already been assigned to other clique indices. Okay, but that's the lower bound. Because so basically, for tree-like resolution, the number of k prime cliques is a lower bound. Done. Are we happy with this? I mean, yeah, this is it. Okay. Now, the interesting thing is that you get essentially the same type of lower bound. For balanced k minus 1 partite, balanced complete k minus 1 partite graphs. Okay, what's a k minus 1 partite graph? We're going to, so you have like k minus 1 clouds. There are no edges within the, so this is a 4 partite graph. No edges within the clouds, but complete, like between any two clouds, you have the complete bipartite graph. And now suppose you want to say that this graph, suppose that you want to say that the clique formula will now say that this graph contains a 5 clique. Okay. So what's my lower bound strategy as defendant? Well, I just pick one vertex here in a linear number of ways, one vertex here in a linear number of ways, one vertex here, and then I play according to the same strategy, right? As soon as I get asked about this vertex and it's consistent to say so, I'll say that this guy is in the clique, this guy is in the clique, this guy is in the clique, this guy is in the clique. And then I'm going to lose when the prosecutor tries to find the fifth clique member, because then I've run out of vertices. But clearly, the only way when prosecutor wins, prosecutor has identified these 4 vertices that I chose, and essentially I can choose those in, well, n over k, choose k different vertices. Does it make sense? Fantastic. So what do we know about general resolution and what do we know about regular resolution? So let me talk about random graphs first, and then about k-1 quartet graphs, because this is an interesting case that it's worth understanding. So for general resolution, there is a paper by Beam, Impagliazzo, and Sabharwal. And they actually prove average case clique lower bounds. So they prove lower bounds exponential in some n to the epsilon for positive epsilon. But k has to be somewhere between n to the 5/6 and n over 3. So these are very, very, very dense graphs and extremely large cliques. So you get these lower bounds for extremely dense Erdős-Rényi random graphs. For k equals to n over 3, you can get exponential in, actually truly exponential in n. But note that this is like the wrong dependence. This is a sort of a 2 to the n lower bound. It's not an, it will then be like a, sorry, it will be a 2 to the k lower bound, not an n to the k lower bound. But nevertheless, I mean, this is a lower bound. For smaller densities, there's nothing in the literature. Nothing known. Now, interestingly, and this is the last thing we do maybe before the break, for regular resolution, k-1 product graphs are easy. In fact, k-1 colorable graphs are easy. So let me try to do a proof by picture of this. Hopefully, there's a lot of notation, but I think proof by picture is kind of a nice way to get the idea across. So let us visualize. Let's suppose we're refuting the 8 clique formula in a 7-partite graph. So let's see. We have V1, V2, V3, V4, V5, V6, and then I need V7 apparently. By the way, I didn't say what a balanced graph is. Let's say that the graph is balanced. So it's so a k-1 partite graph. Let me write this. Complete. What do I mean by this? Well, I mean that there's a partition V1 disjoint partition V2 disjoint partition Vk-1. The edge set is just for all I less than j, you take all edges between vi and vj. Right? This is what this picture says. And now it's balanced if every vi is equal to n over k-1, except that maybe that's not an integer. So either I round it up or I round it down. So basically, all partitions have the same size, except that if k minus 1 doesn't divide n, then obviously I have to do some rounding. Okay. So these are now these vertex sets here. And so there is, okay, so maybe the drawing isn't fully to scale. You should think of these as being, the columns are fairly large now. Whereas the rows are just, these are the clique indices. And now we are going to keep track of how many different configurations, how many different records we will see. And we will crucially use that in the prosecutor-defendant game that we can't forget. But now the important thing is that since we're regular, you should think of now it's a prosecutor-defendant game where you can ask, you can choose to remember, and then you forget. But if you forget a variable, you are screwed. You cannot requery it again. You'd better not need it. Okay. Okay. So now I'm going to start by querying, and let me write 0 for everything that is false. So I'll just fix the highest index k, and I'll just query all the vertices for k. So like, is it over here? And the defendant says no all the time, say no, 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 no. And suddenly maybe over here, or actually let's say without loss of generality, because if there's some symmetry here, we can argue that maybe here I pick up a 1. Like this is clique member number 7. Okay. So the prosecutor first does this, and now, now I know this. Now, given that I have my vertex in V7, what do I know? Well, I know that no other guy in V7 can be in the clique, right? So now I'm just going to query all of these. And if I pick up a 1, then I've won, obviously. So I'm just, and that's a good scenario, but the bad scenario is that I'm just going to fill all of these up with 0. Okay, and note that again, if I ever pick up a 1 here, then we're good, then I've won already. Okay, so now, prosecutor has asked about all of this, and now what am I going to do? Okay, so my legend here is this is a 1, and now my third color blue is going to be forgotten stuff. So now I just say, fine, I'm done. Let me actually forget all of this, everything. I've purged my record from all of these variables. So they're gone now. So now you realize it doesn't matter which one I picked up here. The only thing that matters is which block it is. So there are only 7 possible records now. Here I have like a quadratic number of possible records, but then I just condense and now I'm down to 7 possibilities, k minus 1 possibilities. And if you think about it now, I've ruled out V7 is not part of the game any longer, but my claim is that I have a, whoops, I see now that we're missing a row. That's why you guys are a little bit concerned. This should have been an 8, right? How do I do this? Even this is a 7, 6, 5. Somewhere I need to squeeze something in, maybe here. Maybe here I have a 4. Sorry, I didn't see this. The point is now, when I've done this, the claim is that the remaining 6 blocks are now forming a 7 clique. And I'm not going to argue about, I'm not going to ask about clique index 8 again. That's completely forgotten. I do need to keep the fact that block number 7 is out of the picture. Okay. So now what do I do? Well, now I'll ask about, clique index number 7. And now it turns out that the defendant says 1 already here. So then we know what to do, right? I'm going to ask about all of these guys. Rule out all of block 2. And note that this is now like something like an n squared number of different queries that all depend on that started from potentially different records. But now I'm done. I've ruled out block number 2. So now I just forget everything here. And from now on, we're going to look for a 6 clique with blocks V1, V3, V4, V5, V6. Okay, and then we like, I start asking for V6. I ask here, nothing, nothing here, nothing here. Oops. Apparently here, I picked up a 1. So then I'm going to ask here for all of block V5, all of what remains. And if I ever pick up a 1, then I'm done. So let's suppose I get zeros. Then I fill in this whole block with zeros. And then I forget. Okay. And note now that after I've identified the first 3 clique indices, how many possible records could I have? Well, I've had like an n squared number of possible records along the way, but now I have only basically k minus 1 choose 3 possibilities, right? Because the only thing I care about now is which of these 3 blocks have I ruled out. And that doesn't depend on exactly which these ones are, because those I have forgotten. Does this make sense? So now if we just do the math, how many? So what did we do? So we like the strategy for basically we identify the current clique member, like recursively, say at iteration, when we have maybe iteration L, how many starting positions do we have? Well, we have something like k minus 1 over L. Let's be generous and say k over L. Let's type in. So I have basically k choose L starting positions. Then I just identify the next clique member. That's going to be less than n queries. I'm going to go over all of this row. Once I have identified it, I suppose that this clique member is in block Vj. Ask about xvj for v in vi and all j that are strictly smaller than, well, what are we going to have? It's going to be something like k plus 1 minus L, I guess. How many queries are this going to be? Let's be super generous. I think this is less than k choose n. And then I just forget and go to next stage. Okay, and now the question is, how many records in total are this? Well, this is going to be something like the total number of records is in the Lth round, it's something like k choose L. And then we said first n queries, and depending on the result, k times n maybe. I'm being extremely generous with my counting here, because this works even for non-balanced graphs. And this actually, the same strategy will work for k minus 1 colorable graphs, where you can just think of this as being the color classes. Yeah. So in the iteration L, we had something like k choose L times k times n squared. Now we're just going to sum this up over all L, and this is going to be something like 2 to the k times k times n squared. Except that I'm not sure if we're doing the counting correctly. I think BGL claims a 2 here, but I don't care. It's something along these lines. Are we happy with this? So again, what am I using here? I'm using that the prosecutor-defendant game is in fact a characterization of resolution. Because I just told you the prosecutor strategy. But if you don't believe this, then you will be able to, you can manually turn this into a resolution proof. It's just that it's harder to describe. And the reason why it is regular is that you saw that I'm only asking, I'm asking over variables first for the largest clique index and the next largest clique index, and I'm never revisiting all larger indices. And once I've ruled out the block completely, I'm never revisiting it either. So I'm only querying variables once. The reason why this is good to keep in mind is when you start doing lower bounds. Because at least in my experience, very often you have a nice lower bound strategy this is why k-cliques should be hard. And you start working on it and things are promising, and then after 2 hours, maybe you realize that, oops, I had this rule of thumb that I should always have. Is there anything in this lower bound approach that I have now that will fail for complete k-1 partite graphs? Because note that k-1 partite graphs, they contain, for instance, if your lower bound is just using, there's lots of cliques around. I mean, what could have more cliques than a complete k-1 partite graph? There are cliques all over the place. Really, really large cliques, right, of size k-1. Okay, and often you'd say, okay, because of the density of cliques, here's your lower bound. Well, if what you're doing will work for the k-1 partite graph, then it's not good enough. Because complete k-1 partite graphs are easy for regular resolution. So whatever we come up with has to somehow explain why random graphs, they also contain lots of cliques, but they don't look like this. That's the challenge. Questions before we take a break? And let's take a break. So we are back after the break, and we are going to start doing the lower bound now. And it's going to be what we did before. We're getting rid of interpolation, and we're going back to what we did before. Let me rephrase the lower bounds we had for the pigeonhole principle and for Zetin. Let us think of them, because what we did there for both pigeonhole principle and Zetin is by some somewhat random process, partially random, partially deterministic, based on the randomness. You could view it as we actually looked at the proof tag and we generated a truth value assignment that defined a path through the proof tag. Okay? So generally speaking, we somehow, what we've done so far for pigeonhole principle and Zetin again, we defined some kind of random walk R sub alpha that was somehow tied to a random truth value assignment alpha. And you could view it as then using this alpha to start a walk through the proof from the bottom and going back to sources. Which is the same thing as the prosecutor starting to ask questions to reach a falsified axiom. And then we argued that all of these random paths had to pass through a special bottleneck clause or bottleneck node in the proof. These were the informative records in prosecutor-defendant speak. Okay, and let's say that W is such an informative record. Then we said, okay, but fix any informative record, because this is not random, but our initial alpha is random. And for any fixed bottleneck, let's look at the probability over alpha that the path generated by alpha hits this particular bottleneck W. And we argued that this number was very small. And then we said, great, now we have a lower bound because we hit some bottleneck with probability 1. And if every fixed bottleneck is being hit with very small probability, then that means that there have to be a lot of bottlenecks to hit. Okay? And this is what we're going to do today also. There are going to be 2 twists. Typically, the probability of hitting a bottleneck, like the way, the mindset you have and the tools we have, typically you get concentration of measure and intersections and stuff, and you get exponentially small probability. Clearly, we cannot expect to get exponentially small probability because the proof is of size at most n to the k. So whatever we're going to do has to be sort of fine-tuned enough to actually pick up an inverse polynomial probability, which is a little bit interesting. Because typically, either our tools don't work or they give you an exponentially small probability. But exponentially small is too good to be true. The second twist is that our bottleneck is actually not going to be a single node. It will be a pair of nodes, and our bottleneck is going to be that you pass through both of them. Okay, and now now we need to set up some careful terminology about this. I already said that the branching program will contain nodes. And these are A, B, C. When I talk about the graph, I talk about vertices. They are things like U, V, and W. So whenever, a vertex is about this graph that doesn't contain a k-clique, node is about the branching program that is figuring this out. And from now on, unless stated otherwise, we already said that the regular resolution proof will give me a read-once branching program. From now on, let's just talk about lower bounds for read-once branching programs. So in a read-once branching program, suppose it looks something like this. Actually, it looks maybe more like this. And here you have a lot of different axioms. Let's look at an A somewhere in the middle. Since this is a DAG, there are many different ways of reaching this A, right? And here's the first nice property. Note that if I just define a path, any path, I claim, if you just look at, again, what do the branching nodes look like? You're querying a variable x, and then you take any outgoing edge that is labeled 0 or 1. Any path is a well-defined partial truth value assignment. Note that is not true in general. Right? Already, I'm using the read-once property that any variable is mentioned only once, so any path decides exactly whether x is true or false. Okay? So any way of reaching A will be actually the truth value assignment defined by that path. Which means also that from now on, we're going to be a little bit hazy when I talk about alpha, I sometimes say it's a truth value assignment, I sometimes say it's a path, because they're the same. And in particular, if I find a way to generate a random path, that will also be a way of generating a random truth value assignment. Are we happy with this? Okay. So, and note that I can reach A in very, very different ways. However, I'm going to write beta of alpha is the largest truth value assignment that I will see along any path. Okay, like this is sort of, and I will refer to this as what the branching program remembers at A. Why do I say this? Well, suppose that I queried, something really interesting here that isn't on these other paths. Then once I get here, I don't know this green stuff because it's not on this path, and I know I won't be able to requery because of read once. So if these values were super interesting, too bad, because they're forgotten. The only thing that the branching program knows at this point is beta of A. Is this clear? Okay, that's the definition. So that's the definition of remembering. So let's now make clear this notion of what I don't remember. Let me say that when I define a path, and if this path comes to x and then it walks along the 0 edge, I would say that alpha sets x to 0. Or if I take the 1 edge, I say alpha sets x to 1. Again, it's just going to be the same thing as, walking along edges or setting variables true or false is again the same. This is making terminology precise. Suppose now for A that there exists, one more thing. Just to save typing, I'm going to talk about source paths. Source path is what you see here. Like we always start in the source. So a source path is just any path that starts in the source and then reaches some node. We're going to have paths also inside the read-once branching program. We'll get there later. Source paths always start at the beginning. Okay. So suppose there is a source path alpha that goes to A, and suppose alpha goes to A. Sorry about this. And suppose that alpha has the property that alpha sets x to some value. But suppose that beta of A doesn't contain anything about x. So beta of alpha, the domain of beta of A. Sorry, I'm messing up A and alpha. We have a sort path alpha that reaches the node A. Alpha, this particular path, this one maybe, sets x here, but there are other paths that don't set x. So beta of A doesn't contain x in its domain. Then I say that x is forgotten. At the node A. And here comes a first easy observation. Suppose that, if x is forgotten at A, and suppose that there is a path from A to B, then I claim that x is forgotten at B also. Are you with me? So let's do a proof by picture. Suppose not, okay? Well, we know that here is the path since it is forgotten, there is some alpha prime here that actually queries about x over here, but there is some alpha that doesn't query x. The only way that x would not be forgotten at B is that x is queried over here along some path, right? In fact, along. But now you realize that, because if that is the case, then taking alpha and then some path gamma, say here, now I have queried x, and now I could potentially have x in beta of B. But then obviously this path is querying x twice. I'm actually maybe beating a little bit around the bush for something that is obvious. Are we happy with this? Okay. But note that already we're using, note that this is like super false if this was a general resolution proof. So we're using that it's a regular resolution proof. Now, this is all in full generality. From now, let's focus on clique formulas. Let me say that if XVI is forgotten, at A for some V, so fix I, that's what I care about. If there's some vertex V such that XVI is forgotten at I, then I say that the index is forgotten. Index I is forgotten at A. Okay. Now, one final piece of notation: if a source path alpha ends at a node labeled by a clique axiom, here it is, XVI for all V in V, then I say that alpha rules out I. Okay, and now I want to just tie together everything we have so far in another simple observation. This was observation 1. Here is observation 2. If a source path alpha rules out the index I at the sync node B, then I is not forgotten at B. Okay, why? Well, this is kind of just putting together the terminology so far. The point is that if alpha ends in B and B is labeled by the ith clique axiom, then we know that all paths to the sync B have to set all of these variables to false. So B, beta of B contains XVI false for all B, which means that by definition, the maximum B, beta of B does contain all of these being false, so they're not forgotten. Right? Another way of seeing this is, and maybe a way of flipping this around is, suppose that here you asked about XVI here, and then we come to A and A is forgotten. Then what can I say? Well, anything that I can reach from A, whatever the branching program does, it's not going to find a violation with clique axiom for clique member I. So if this index I is forgotten here, then you realize that it's always, the branching program will never be able to tell, well, maybe vertex V was the ith clique member. What do I know? And I'm not allowed to ask. So clearly I cannot claim that the clique axiom for clique member I is violated if I have forgotten some XVI. Okay? Are we happy with this? Okay, so from now on, just so now let's fix a read once branching program. Capital pi. So my proofs are usually lowercase pi. A branching program is an uppercase pi. And it solves the clique formula. For G and K. But without, and there are no ordering constraints, so we only have clique axioms, edge axiom, functionality axioms. G is k-clique free. Okay. I want to show. Okay, so let me say, in fact, let me say more than a J is k-clique free. We're saying that suppose J is sampled with the parameters as in the theorem statement. So minus 2n to the minus 2 eta over k minus 1 is the edge density. What we want to show now, we want to show that pi has size n to the big omega of k. And I'm going to define a random distribution over the read once branching program. And we want to walk over it and we want to identify bottlenecks, except bottlenecks are going to be pairs. And then we want to argue that, so that means that I'm going to lose a square root, right? Because that means that a branching program of size whatever, it's going to have like size pi squared bottlenecks, but we're not worrying about squares here, or like, because that factor too, I'll happily just fold into this. So maybe let me write the random distribution over here, because now it's kind of clear what we're doing with the bottleneck counting. And I should say, by the way, that I'll tell you when we start crashing. So far, like all the details so far are good. So maybe let's see let's see how far we get today. Maybe we won't say anything broken today. That depends a little bit. So far, everything is good, but we might need to remember. So we're going to define a distribution calligraphic D over paths. And again, I can think of the objects sampled here. They're going to be paths in the read-once branching program, which means there are going to be truth value assignments. Same thing, right? And we start with the source node. And then we're just going to generate the random walk one step at a time. So we are at the current node A. So we've done this now step by step. And the current node at the beginning is contradiction. So the start node. We'll do the following. So the current node is asking about A is querying. Oops, sorry. At current node A, and A is querying X, V, I. Okay. So I have to now pick. So the way I'm going to generate my random walk, obviously, I need to pick a random value now to XVI. Am I going to take the 0 edge or the 1 edge? That's all I need to do, and then I'll end up at a new node, and then I'll do the same thing again. Okay? So I will look at everything, what the branching program remembers here. Okay, and obviously this I can compute, right? I mean, we have fixed the pi, so every node we know that what it remembers. So I don't care about the exact path so far. I want to know what would any path having gotten to this place. What would any path remember? Well, if I take bi, and if extending it with XVI goes to 1, if that falsifies an edge or a functionality axiom, then we take the 0 edge. Okay, so because this is an immediate contradiction, it seems stupid. No, we're gonna, like, intuitively, I want the walk to continue. And I know I'm going to cause an immediate contradiction, so that's the bad thing to do. Okay? If I is forgotten at A, then I also take the 0 edge. Because this means that apparently some paths have already queried other vertices for I, but then forgotten about their values. So then I will have plausible deniability. I sort of already know that the branching program, given that I is forgotten at A, will have to do something other smarter. So it's like safe for me to say, no, V is not the ith clique number. I would be stupid not to say 0 here. It's a safe choice because I won't violate clique axiom I. Except the problem so far, there's not too much randomness in here. So that comes now. So let me refer to some terminology on the fly here. I will refer to these as forced choices. There's nothing random about these choices. Like, based on what the branching program has already done, I'm just saying, well, not much to think about. I'll just commit to this. However, now I'm in a situation where setting V to be a clique member is fine, at least locally. And it could actually be, I mean, and it's not necessarily safe to set it to 0, because you maybe it is conceivable that we will end in a node pretty close that will actually violate this side. Maybe it could be, in fact, that there are very few alternatives left. You know, maybe I've ruled out all but a few possible clique members for I. So it's not entirely safe to say 0. So I'm sort of, and now what I could do here is I could look at the graph and I could compute. I know B of A tells me what I know about the graph, the residual graph at this point. So I could try to do something smart, right? And try to compute, like, based on how many, you know, what is the current candidate clique that beta of A identifies, given this, how intelligent would it be to extend it with V as opposed to kicking the can down the road and hope that it will ask for something else? We could try to do something smart here, yes? But we won't, because I don't know how to do it. So we'll just flip a coin. That's the best we can do. But it's clear that if you flip a coin, should the coin be like a 50-50? But the choices are highly symmetric, right? Just as for if you think about the pigeon axioms, like saying that V is not the ith clique axiom, is not the ith clique member, that's not revealing too much information. But saying that V is in the clique, then suddenly we know that, okay, we're now, for the rest of the branching program, we're just going to play on the neighborhood of this particular vertex. So it doesn't seem like 50-50 is probably a bad idea. Okay, so we're going to flip an n to the minus delta biased coin. Let's discuss exactly what delta is later. Delta is some positive constant. And I'm going to set XVI to 1 with probability, I guess, n to the minus delta. And I'm going to set XVI to false with probability 1 minus n to the minus delta. So it's going to be super probable that I probably set it to false. But, you know, but every once in a while I set it to true. And this I will refer to as a free choice or as a coin flip, because, well, it is a coin flip. Modulo that I haven't told you how to pick the delta. This is it. This is our random walk. Now we just want to identify bottlenecks in this and argue that bottlenecks are that we're unlikely to hit bottlenecks. Let me make maybe an observation about this. And this observation is going to remain true, because up to this point, this is, you know, except that I haven't told you exactly how to pick delta, this is the random distribution that we're going to explore. And you can say, like, is this really the best we could do in C, just to flip a random coin? A very good question. But the point is that the fact that it's a completely random independent coin flip, that's going to help us later on. Because suppose we sort of try to use the structure of the graph here, then the probabilistic analysis gets a little bit hairy. we're going to use heavily that these are independent quotients. But like potentially you could do something smarter. I don't know. So observation, two observations about this. Any alpha sampled according to this distribution. And let me warn you that from here on, I'm going to be a little bit overloading notation a little bit. I'll write alpha tilde d to actually say that alpha is sampled according to d with the right probability. But sometimes it will just mean that alpha is in the support of the distribution. And hopefully it's clear from context with which one of the two I mean. Here I'm just saying that any alpha in the support of this distribution ends by ruling out some index I. Okay. That is, my path alpha will never hit an edge or functionality axiom. It always hits a clique axiom. Are you happy with this? Because, I mean, why is this? Well, whenever we risk hitting an edge or a functionality axiom, we just say, no, it's false. Right? Whenever we're at a situation where one of these two guys could become false, we just set the remaining literal to false. We're never going to violate this. We happy with this? And the other crucial observation is that any alpha in the support of D sets at most k variables to 1. Why? Actually, let me be. I'm a little bit generous here. I'll sharpen the bound a little bit. Why is that?
Yeah, because you will never violate the functionality action. So you're not going to set two vertices for the same clique member.
I'm never going to set two vertices for the same clique member, and there is no k-clique. So the only other way I could set more than k1s is that I've actually found a k-clique. But there are no k-cliques. Okay? So this gives the following idea. So for any alpha in D, we define waypoints along the path. So here's alpha. So I'm gonna pick out alpha A0 is the starting point, and then I'm gonna have alpha 1, A1, A2, ... up to some A T prime, or T prime at most being T. And the way I define these waypoints is, again, A0 is the source, contradiction. A sub I plus 1 is the first time after AI when we have K over T additional assignments of variables to true, X, V, I being set to true. or it could also be the sink, whatever comes fast, well, whatever comes first. I mean, at some point over here, I hit the sink, and then I just, that will be the last vertex. Okay. What is t going to be? It's going to be a parameter. We'll talk about it later. We've now entered the territory where, let's see how we're doing on time. Actually, maybe we can, let's see how much we can do. We can almost crash if we're fast. Okay, so note now that suppose that alpha, in fact, rules out the index I. Then let Vi be the vertices such that x Vi is set to 0 between AI minus 1 and AI. Okay. So suppose this path actually ends by ruling out index I. Let Vi be over here. I just look at what variables xvi are being set to false here, and let that be, this is V2 here. Okay. Then I claim that V, all vertices V in the graph, is in fact the disjoint union. It's a partition of all these V1, V2 up to Vt prime. You happy with this? Okay, but now there exists a J such that the size of Vj is at least n over t. Round up if you like. Right? Just by, I mean, we're cutting it up into at most t parts. And we know that when we've gotten to the end, we've ruled out all n vertices for clique I. So somewhere, if I'm chopping it up into at most t parts, somewhere I'm doing more than a 1/t fraction. Happy with this? And this is interesting. Suppose this happens here. That means that here, actually, the way to think about this is the branching program is making a lot of progress at forcing contradiction here. So I'm going to call, suppose that this is Vj. This Vj such that Vj is of size of most n over t. And I'm going to zoom in on Aj minus 1, this guy, and Aj, which is this guy. And I'm going to call this pair a useful pair. Except I'm going to call it useful with a star, because this is going to crash. We're about to crash now. Okay. What we hope is that these are going to be our bottlenecks. So we want to argue that clearly we're making sort of a lot of progress when we go from Aj minus 1 to Aj. And to some extent, we want to argue that, yeah, so like, what would the idea be? Why would this work? Well, to be sure, we are always, suppose that a bunch of these coin flips are free. Then, of course, like 0 is a very likely outcome, yes? But still, it's a linear fraction of coin flips that come up 0. Like, surely every once in a while we should see a 1. At least if the coin flips are free. And so depending on how delta n to the delta compares to the size of Vj, maybe not seeing any V in this interval is highly unlikely. That's the hope. Okay, let's see if we can pin this down. But the first thing I want to say is that we have proven, I claim we've proven the following. That any path sampled according to D passes through a useful pair with probability 1. This is true, right? I mean, we where did we do the proof? I guess here we did the proof. Is it a typo or?
No, maybe just so does the two i's in the definition of vi and in the statement suppose A rules out I, is that two different i's?
This I
Yes.
is the same as this I.
Then there are eyes in the definition of that set.
Yeah, exactly. Because we're picking out all the V's. So this path rules out the index I.
Yeah.
What does that mean? For every V, it will set XVI to false.
Yeah.
So I is fixed here, and VI is the subset of vertices V such that the branching program sets XVI to false during the signal.
Yeah, but it also says it happens between AI minus 1 and AI. So it's also both location and also what gets ruled out.
This is a J. Thank you. Yes. Thanks. Yeah, we switched to a J down here. Okay, good. Thank you so much. Any other confusing typos? Or are we good now? Makes more sense?
Yes.
Thank you again.
Okay. Define useful.
Say again?
You only define useful in words.
If Vj
the pair
is larger than n over t, then aj minus 1 aj is useful. That's my definition. Good. So are we clear? And then we just argue. So a useful segment or a useful pair is just with respect to alpha, is that we zeroed out a lot of XVIs on this segment of the path. Like at least a fraction, a 1 over t fraction for this parameter t that we haven't yet fixed.
So ruling out the things is the progress.
The progress measure is so we know that we're looking at a path alpha that will end by ruling out I. So the path I will end by falsifying this axiom. We know that we know the way we're sampling the paths, they're always ending by ruling out the clique axiom. They're just fix alpha, look at which I it is focusing on. So we already know that that's going to be the final target. Now let's measure progress. And the progress is going to be like, how many I's are we ruling out? How many V's are we ruling out for this clique index I? Okay. So here's a crucial observation. Suppose there exists one path, some path, that has the following property. Alpha passes through AB. So it passes through A and then later it passes through B. Suppose that alpha sets X V I to false for, by definition, V in this Vj. Or suppose that, yeah, okay. And suppose that actually this is any VJ now. I could maybe I'll just, to stress this, let me call it capital W. Suppose alpha rules out index I. Then I claim that any alpha through A and B has to set X, V, I to false for V in W between A and B. This is absolutely crucial. Okay, proof by picture. So here is our path alpha. Here are two waypoints. We know that we rule out I here. Okay. Now, actually, didn't use orange so far today. So let's go with orange. Suppose now that we have some other path here, or some path like this. Okay. Then clearly going from here to here and then taking this orange path and then continuing is also valid. Or taking this orange path. Okay. So in particular, both of these orange paths also have to rule out I. So they have to set all XVI to false. But they cannot query anything in W here or here, right? Because that would violate the read once property. So actually, once I know that alpha rules out I here, then any subpath between these two guys have to rule out the same zeros. This is like super important. Can we say this again? So again, the point is just that you do this path substitution trick. Just swap out from here, you take this path, and then you continue. And now you can say, well, how do I even know that I can take this path? Well, again, I'm using, like, maybe this contradicts this, right? No, there's no, like, one part of the path can never contradict another part of the path, because then it would set the variable in two different ways. So like any way of composing path segments will yield a valid assignment. Okay. And so in particular, walking from here and then taking this path and then walking here is an assignment that by construction violate the ith clique axiom, but also satisfied read once. So all XVIs are set to false, but by read once, if one path between these two guys sets a particular set W for X, for V and W, it sets XVI to false, then any path segment between these two has to do the same thing. Questions about this? I don't see enough happiness.
I understood what you said when you were talking about the picture, but I don't understand what you've written.
Okay, so let me see, like, what have I written the same thing? So suppose here's alpha is the blue path. Suppose alpha passes through A and B. Here's A, here's B. Suppose that alpha sets XVI to 0 for V and W between A and B. Maybe that was, I had this index J there before this. So yeah, so this was not super clear. So in particular, like here on alpha, what is happening here is XVI is set to false for all V and W. Okay. And suppose that alpha goes on to finally rule out index I, importantly. Then any way of getting between these two vertices has to rule out. I mean, it can query a lot of other vertices for, you know, for, I don't know, U and W and I don't know, but all XVIs. So in fact, I'm going to get like the picture I'm going to get for these waypoints and why they make sense is like between two waypoints, I know that they're going to rule out exactly the same vertices for index I, if that is the index ruled out in the end. And this is like a super nice property. But it's an extremely read once property. Okay, and now we want to get to a point where we can wrap up. So let me see. We have observation 5. What am I going to do? Maybe I'll just. So let me hand wave what's going to happen. And then because we can do all the calculation next time. Whoops. Things are breaking in a major way. So, okay, so I claim up to here we actually did everything. Like up to here, everything is true. So now my hopeful claim is the following. For any fixed AB that are two vertices in our branching program, the probability when sampling a path according to D that AB is useful with a star for alpha is n to the minus is less equal n to the minus big omega k. If we can do this, then we're done, right? Because now we have so we have 3 cases actually. If alpha beta is not useful at all, then we're very happy. I mean, then the probability is 0, which is in particular smaller than we want. Case 2 is suppose let's look at what we remember at node A, and suppose that beta of A contains like a linear in k fraction of assignments x v I. This is now any I, not our fixed I, goes to 1. Okay. So the branching program has actually identified a big omega of k-clique. This should make us nervous, because if you know that large clique, then it's not very surprising that you're seeing a lot of, I mean, once you have that many vertices in your clique, there's going to be tons of non-neighbors, and maybe all of them were in VJ. Right, so this is like, doesn't seem good, but what saves us is, well, it's very unlikely that alpha reaches such an A. Why is this? Yes?
You said once with small probability.
Yes. And once we always set them with small probability and completely independently. Note that when setting once, we didn't do any analysis about the graphs or anything. It's just a random coin flip. Okay. So basically the probability of getting S once is exactly n to the minus delta S. Okay, and now S is like big omega of k. So this is the, so we're just saying screw the useful pair. Like even hitting A is very unlikely. The probability is n to the minus k to even get to A. Never mind the probability of getting onwards to B. So we're in good shape. Okay. So excellent. So case 3, and now I promise to wrap up. Case 3 is that beta of A contains few ones. Okay. Now what we want to argue is, okay, so it contains few ones, but we will get an n over t number of zeros between A and B. And now suppose, maybe not all of them are fixed, but suppose that are forced, but suppose that n to the gamma of them are free coin flips, free choices. Okay. And then I claim that the probability of all zeros is then going to be something like n1 minus, oops, let's see what we get. n1 minus n to the minus delta raised to the power of n to the gamma. And now if suppose that gamma is like clearly larger than delta, then this is going to be something like, exponential in minus n to the gamma minus delta, just by plugging this in, and we're done. And we can take a break and go. Okay. And the only problem is, where so far did we use that the graph was not k-1 part x? Or where did we use actually anything about the graph at all? So everything works. Everything we've done, so modulo like that, we maybe need to discuss a few constants here and there. But here, things just totally crash and burn. In particular, notice that when we did our upper bound for balanced k-1, complete k-1 part x graphs, once we picked up ones, then there were like a linear number of zeros that we're just massively pushing through. Okay. So in general, this is not true at all, and this is where we crash and burn. But on the bright side, we haven't really used anything about the graph, have we? So somehow we need to argue that when we get to this setting, it's kind of unlikely that the graph will be structured enough that if we have only a small, basically what do we want? If you only have a small clique identified so far, then with a small clique, you should not be able to force tons of zeros. Note that, again, this failed in the complete k-1 part x graph. I had an extremely small clique, just one single vertex. Then I ruled out everything in the same part of the partition, right? I want to say that this cannot happen. So if I have a small clique, I want to say that a small clique can be extended in many, many different ways. So that actually I'm going to get something like n to the gamma free choices. And then I'm going to do this calculation a bit more carefully and things are going to be fine. But like one other reason why you can see that this is too good to be true is that, well, I mean, this probability is like a little bit too good to be true. We're getting exponential over 1/4. So, and what do we need to do? So we need to analyze the structure of random graphs. And it turns out that usefulness, just saying like how many zeros I got, that's a little bit naive measure. Because, if many of the zeros were just forced, then I wasn't making tons of progress. So I need a little better, I need a better notion of progress, of usefulness. And then I need to analyze the graph structure. And then we can prove a low block. But this is, and this I think will, it turns out that this will require quite some work, and so it will keep us busy, I think, for most of Monday. We'll maybe review this a little bit and then see how we can fix this. But this is it for today. Any final questions before we wrap up?
Yeah, about observation 5. So it's any path through A and B that coincides with alpha before A and after B?
No, because I don't care. I'm just talking about the paths here. I'm just talking about the subpath segment, because once, it suffices that alpha exists, because then I can take alpha up to this point and then take the segment I'm talking about and then continue on up.
Okay, yes.
So this is, yeah. So this is really like very, very locally, just looking at all paths between here and here. But again, what I'm using is that there is a blue path that from here will get to the point where it rules out the IF clique membership axiom. Note that there could be, like, you could go here and rule out maybe I prime. I'm not saying anything about this, but I'm just using this. There's one path that rules out I, and by that is sufficient to say that any segment of this path has to rule out the same vertices for I. It's like a super strong, super nice structural property. But again, I cannot emphasize enough that this heavily uses read once. Other questions? And let's wrap it up. Thanks.